Welcome back. Today's topic is problems on computation of potential and electric fields due to electric dipole. In the last video lectures, we have gone through the concept of electric dipole, and we have also developed expressions for determining the potential and also electric fields due to electric dipole. So I hope that by the end of this present video lecture, you will be able to solve simple problems on computation of potential and electrostatic fields due to an electric dipole. We'll solve 3 problems in today's video lecture. Let's go back to the first problem. The question states that find the potential due to a dipole consisting of a positive charge at this point and a negative charge at this point, and at a distant point P in spherical coordinates. So he wants to find out the potential due to a dipole consisting of 2 charges at a distant point in spherical coordinates, which means that there are 2 points plus q and minus q. The coordinates have been given here. So this combination completely is called as a dipole, right? They are separated by some distance. So this dipole now, it is creating an electric field around it, and at a distant point, let us suppose there is a distant point which is in terms of spherical coordinates. So he wants to determine what is the potential due to this dipole. So this is the question. So how to solve this problem now? Now we will start with the basic concepts. Now given the dipole consists of 2 charges plus q and minus q, which are separated by a distance d. See, in plus q they have already said that it is at d by 2 comma 0 comma 0, and minus q is at d by 2 comma 0 comma 0. I'll assume that these are xyz coordinates. So what is the distance between these two? You know the distance between these two. Square root of x1 minus x2 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. So if you substitute, this one is x1 y1 z1, this is x2 y2 z2, what you will be getting? Sorry, this is at minus d by 2, right? Okay, so you will be getting d by 2 into 2. So it will be d. So that's what I have mentioned here, separated by a distance d. So now the dipole is like this, plus q and minus q, both are separated by, it is lying on x-axis and it is separated by a distance of d. So what is the dipole moment of this one? So dipole moment m is equal to q into d. And if you want to take it as a vector, you know that m bar is equal to q into d into unity vector across x-axis. Now, in the previous section, we have tried to determine the potential due to a dipole, where we have obtained an expression of V is equal to, say, this is the expression, V is equal to m cos theta 4 pi epsilon r square. But literally speaking, if you want to write it as a vector, you know, this m cos theta, I will write it as m dot ux, which is nothing but this is a dot product, right? So, which means that magnitude of m, magnitude of ux bar into cos theta, where theta is the angle between this dipole moment and this unity vector, right? So unity vector magnitude is always 1. So what I can write, this is m cos theta. This is what the expression is actually. So if you want to write it as a vector format, then automatically this will become m bar dot ux bar by 4 pi epsilon r square. This was the actual equation. Okay, now I will extend this equation. See, this is the equation. So I will try to extend this equation into spherical coordinates, because he is mentioning that the point is now in spherical coordinates P. So I will try to convert this one into a spherical coordinate system. See, this is a point. So he has mentioned this one. So this will be the radius, this will be solid angle, this will be the angle. Now We know that in spherical coordinates, if any vector is there in Cartesian coordinates, and how to transform it into spherical coordinates. We do have this matrix format, which we have discussed in our CDT3, right? So these are the vector components. It is just like okay, if these are the XYZ components, then automatically so this was theta, this is phi. So transforming this Cartesian coordinates into spherical coordinates, we will employ this particular equation. Okay, now what I assume that I have previously taken that since, if you carefully see, my dipole was lying on x-axis, right? Because the coordinates were only d by 2 and minus d by 2. The rest x and y coordinates were 0. So I have assumed that my v was along x-axis only. Okay, so I haven't considered any other thing. So that's why I'll consider only x component here. The x component here it is ux, and these are 0 and 0. I don't have any y component and z components. And here I'll assume that the field is directed towards the r axis. Okay, the field is directed towards the r axis, which we have seen in the last slide. So I don't consider this angles. So if I substitute them, so what is my equation now? See, ur is equal to sine theta cos phi into ux bar plus this one into this one into this one, right? So the rest of all 0, what I will be getting, this is my expression. Ur bar is equal to sine theta cos phi into ux bar. So just I am transforming the vector from Cartesian coordinates to spherical coordinates. So my earlier expression, which was this one, now converting it into spherical coordinates, what I will be getting instead of ux, what I will be getting, I will be getting ur, which is equal to sine theta cos phi of x. Okay. So now, okay. Now if you carefully see, m value I know already, it is q into d. Sine theta cos phi I do have 4 pi epsilon r square. So my final expression for voltage in terms of spherical coordinates is qd sine theta cos phi by 4 pi r square, where d is the distance between the two charges. Theta and phi are the representations of the point p, r, theta, phi. Okay. Now, having discussed these things, now we will move on to the next problem. Find the potential at a point r is equal to 10, theta is equal to 60, phi is equal to 0 due to a dipole with q charge value, and there is another charge minus 100 nanocoulombs at this point, which means that there are two charges. One is 100 nanocoulombs. There is another charge which is minus 100 nanocoulombs. Both are located at 0.0005, 0, 0. Here it is located at minus 0.0005, 0, 0. And you do have a point P, which is at r is equal to 10, theta is equal to 60 degrees, and phi is equal to 0 degrees. So you want to determine, this is a dipole, okay? So what is the distance between them? That you can easily compute. And you need to determine the potential because of these things. Now we will try to determine this. Now, see now, the charges given are 100 nanocoulombs, and both the charge. One is plus 100 nanocoulombs, the other one is minus 100 nanocoulombs. And the distance between these 2 points is, as I have already mentioned, see these are the, right, these are the points. So you know the distance between them. you know the distance between them, how it is calculated. Square root of x1 minus x2 whole square plus y2 minus y1 whole square plus z1 minus z2 whole square. And if you do it, what you will be getting? You will be getting 0.001. Okay, this is what I have mentioned here. So both are separated by a distance of 0.001. And p value at which you are supposed to determine the potential is already given for you. So we already have the equation which we have derived in the last problem. So what was the equation? This was the equation. V is equal to qd into sine theta cos pi by 4 pi epsilon r square. You know the values of q, its value is 100 nanocoulombs, and d value it was 0.001, and theta it is 60 degrees, phi value it is 0 degrees. I will substitute that. Epsilon value you know 8.85 10 to the power of minus 12. R you know it's 10. You substitute it, you will be getting 7.785 millivolts. Okay, so one more problem we will try to do. There are two dipoles, each is having a dipole moment minus 5 az, 9 az, and these are located at points. These are the points. Find the potential at origin. So there are two dipoles now. You need to determine the potential at the origin. Okay, which means that there are two dipoles already. This is one dipole, this is another dipole, and you want to determine the potential due to these two dipoles. What I will be applying? I will be applying, let us suppose this is V1, this is V2. Total V is nothing but V1 plus V2 because the potential obeys superposition theorem. So first of all, let the position of the charge, sorry, this is not charge, this is dipole. Let the position of the dipole 1 is this one. Let the position of the dipole 2 is this one. It is 0, 0, minus 2, and the other one is 0, 0, 3. So at which point I am supposed to determine the potential? It is origin, right? So I feel that entire thing is now in Cartesian coordinate systems. Nobody has mentioned anywhere. So I'll directly go with Cartesian coordinate systems itself. So I'll assume Cartesian coordinate system, and we know that the dipole, if it is along x-axis, the potential will be given by this vector. Now what he has done, he has given the dipoles lying along z-axis, and he has mentioned z coordinates only. So I'll just convert it into, I'll just take it as z-axis instead of x-axis. So m dot uz by 4 pi epsilon r square. Now first of all we will try to utilize the first charge. So what is m1? m1 is nothing but, this is m1 minus 5 into 10 to the power of minus 9, right? Minus 5 into 10 to the power of minus 9, nano is there, into uz bar. I mean this is az, right? So I have written as uz, and here I want to do it with this is unity vector along z-axis, right? So how to determine the unity vector along z-axis? See, this is dipole 1, this is dipole 2, and this is my point, right? So unity vector along z-axis means, first of all, what I will do is nothing but, before going for this, I will take it as dl vector itself, unity vector across dl, across the entire length. Okay, so across the entire length I will do. So what is the entire length basically? It will be unity vector across the line joining the two. It will be x1 minus x2 into ux bar plus y1 minus y2 by ui bar plus z1 minus z2 into uz bar by unity vector I wanted. So I will divide it with its magnitude. And here 4 pi epsilon, I know it's r1, I know it because from the origin, what is the distance? This itself is a distance. So I have done it 2 square. So what I will be getting here? It is minus 5 into 10 to the power of minus 9 uz by, this is, it remains the same. So here what I will be getting? I will be getting 2 uz by, its magnitude is again 2. So I will cancel this thing, uz dot uz, I will take it as a 1. So my answer will be minus 11.25. In the second case, again, I will do it with the dl, unity vector along L. So unity vector along length for the second point, it is at 0, 0, 3, right? This is at 0, 0, 0. So 0 minus 0 into ux bar, 0 minus 0 into uy bar, 0 minus 3 into uz bar by square root of its magnitude, it will be 3. So if I do this one, so here I will be getting, if you carefully observe, I will be getting minus 3. Earlier, this point was at 0, 0, minus 2. So when I have done here, I have got only 2 uz bar, but here I will be getting minus 3 uz bar. You should note down the difference between these two. Okay, minus 3 uz bar. So it will be minus 9 volts. So if I join these two using superposition theorem, for the first case it was minus 11.925, second case it's 9. So I'll be getting minus 20.25 volts. So this is the way how we compute potentials. Two dipole moments have been given. Okay. So if you want for easy understanding, we have tried different values, right? Next we tried it as m bar dot uz bar. So if you are getting confused with all these things, you do one thing. You try it as v is equal to m bar dot u l bar, where ul is nothing but unity vector. Ul bar is unity vector along line joining points and a dipole, center of dipole. If center of dipole is not given, then you take the dipole itself. Okay. Sometimes center will be precisely given, otherwise dipole coordinates only will be given. So it is a unity vector along line joining point and dipole. Okay. So this is it for today. In the next video class, we will see behavior of different materials in electrostatic fields. Thank you. And I hope that now you are able to compute electric potential and electric field intensity due to a dipole. And this is a homework problem for you. See, there is an electric field which has been given for you, which is in picocoulombs per meter. It is located at origin. Find V and E at the points. I hope that you can easily solve these type of problems. We have already done expressions for electric field intensity. We have done this one, right? So we practice these problems at home and get back the answers by tomorrow. Thank you.